Okay, so the whole rest of the course is quadratics, quadratics, quadratics. Just like in grade 9, it was lines, 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 what seemed like forever, okay? But it does change. It's not just all the same thing the whole time. So we've got 3 short, well, they're usually longer, but 3 shortish units based on the fact that we're in math all day. And the first one is our introduction to quadratics, and today we're going to learn about standard form of a quadratic and the vertex form of a quadratic. Okay? Tomorrow we're going to continue on with the vertex form and learn something algebraic for Friday, and then when we come back, we'll build on that and we'll learn a third form. And the first intro is just to get comfortable with the 3 forms. Okay? And then we move on to something different in our second unit on quadratics. Okay? All right, so our learning goal is to distinguish between the basic properties of a linear relationship. So from last year, linear, we all know that. And a quadratic relationship, that's what we're learning this year. And we're learning the basic properties of a quadratic relationship. So if we go back to grade 9, this is an equation of a line, and it's because the exponents on the x and the y are both 1. Okay, that's how we came from an equation that we were dealing with a line. If there was an x and y and the exponents on them were both 1. And this you can think of as the easiest line there is, okay? Y equals x. So if x is -3, y is -3, because y equals x. Okay? If x is -2, y is -2. If x is -1, y is -1. And then if we were going to draw that on a graph, this set of ordered pairs, they're going to line up in that line that goes, so 3, 3, 2, 2, 1, 1, 0, 0, -1, -1, like that. And then you can take your ruler and draw your line in. And if you remember, even from our first unit, so a couple weeks ago, the slope of this line is the number in front of x, so the slope is 1. And if you look on your graph here, your rise is 1 and your run is 1, right? So your slope is 1. And our y-intercept is 0. That's why you don't see a plus b part here, a +5 or a -5 or anything. Okay, that's why the y-intercept is 0. So with a line, you're defined by your slope and your y-intercept. Okay. First differences, you probably remember doing this a ton in grade 9 as well. So how you get from -3 to -2, add 1. Remember doing this in grade 9? Add 1 over and over again. Sometimes it was add 5, sometimes it was add 100, depending on the question. And then you would also do it on this side. And this always turned out to be the rise, and this always turned out to be the run, and then you could divide them. Remember that? Not really? It's kind of a haze. It is a long time ago. How many people learned grade 9 in COVID? Distance learning. Wow. Is there a high functioning class for learning most of your math in COVID? You must have done a high level of participation. That's awesome. Shape of the graph. So the shape of the graph is a line. Okay? Defining characteristics. We know that. Slope. M, which is the rise over the run. And the y-intercept. B. Okay, I'll also have names like initial value. Fixed part. Can go on and on. Forms of equations. So we had our favorite, which was y equals mx plus b. Okay, that was our graphing friendly format. And then there was also this one called standard form, which if you take calculus and vectors, you'll finally see why that's such an important form. But for now, it's probably just an annoying form for most people. But it did help us model word problems in linear systems, I guess. And the first differences from the y column, first differences were the rise, and the x column, first differences were the run, and it gave you a way to find the slope. Okay? And the first differences for a linear relationship are constant. Linear has constant first differences. So that's an important part there to note to yourself that a linear relationship has constant first differences. Okay? Because we're going to see what happens with the quadratic. They won't have constant first differences. Okay? It's a way to tell. So this is kind of like linear, tiny little summary of line, right? What does the table look like? What does its graph look like? What are its features? What do its equations look like? What do the first differences mean? All right, so on to our new quadratic relationship. So our big relationship that we're studying for the rest of the semester. The most basic one of these quadratics is y equals x squared. And you can tell it's not a line because x is squared. It's got that power of 2 on it. Okay? So that's how you tell that it's a quadratic and not a line. X has a squared on it. Okay? Let's make its table of values then. So if I put -3 in for x, I'd be thinking to myself, I'm replacing x with -3 and squaring it. What am I going to get? 9. If I replace x with -2 and square it, 4. I square -1, square 0, I still get 0. Square 1, I get 1. Square 2, I get 4. And square 3, I get 9. So you kind of notice this pattern here. You see how those are the same? And then these are the same. And then these are the same. And then there's one in the middle. Okay, that's good. That's going to mean something to us shortly. All right, so let's draw a graph of it from the table. So -3 and 9. -3 and 9. -2 and 4. -1 and 1. 0 and 0. 1 and 1. 2 and 4. 3 and 9. Everyone see that? So this is not, you don't join them with a ruler point to point. It's supposed to be a smooth U-shaped curve. A smooth U-shaped curve. So as we draw them 100 times by the end of the course, you'll get really good at drawing them. Your first one may not look too nice. Even mine doesn't look that nice. I get better too as I keep drawing them. So this U-shaped curve is not called a line, obviously. It has a special name called a parabola. Okay, so the name of that U-shaped curve is a parabola. It doesn't have a slope and a y-intercept as defining things. It has a vertex. Where do you think the vertex would be if you had to pick a spot? Down here? Yes. Okay, that's our vertex. So where it changes direction from decreasing to increasing, okay, most people can see there, they call it the bottom, all right, whatever, where everyone see that that's what the vertex is, and it's a point. The vertex is a point, so it has an x and a y. In this case, we usually use capital V for vertex, And the coordinates for the very simplest parabola, the coordinates of the vertex are 0, 0. Okay? It also doesn't have a slope. The only thing we can call that's similar to the slope we call the step pattern, which is kind of a weird thing to call it. So starting at the vertex, do you see that for me to get from the vertex to the next point that fits on a corner, I go over 1 and up 1? And I do that on both sides because it's symmetric. Okay? So my step pattern is over 1, up 1. That's my first step. What's my second step? So to get from this point to the next point that's on a corner, I go over 1 and up 3. So that's my next step. And then to get from the next point that's on a corner to the next one that's on a corner, I go over 1 and up. Yep. Anyone have a guess that what would happen next? Yes, it does follow that pattern. Okay, then it would be 9, 11. Everybody get that? So that's the regular step pattern. That's the regular one. So instead of writing this up when I'm asking for the step pattern, if it's the regular one, even if it's not, your little shorthand for it will be will be up, because they can also face down. So up, and then you're just going to write 1, 3, 5, ... Okay? So that's how you're going to tell me the step property without having to write that out. And when you write that out, that's going to mean to you from the vertex you go over 1 up 1, over 1 up 3, over 1 up 5. Okay? On both sides. Everybody good? So the shape of the graph, so let's fill that in down here. We've got a parabola. Defining characteristics of vertex. Okay? And it will be some point xy and a step pattern. I think I am, yeah. I am. A step pattern, which for the most basic one, we decided was up 1, 3, 5, but we'll learn how it can change. We'll learn how to change it.
Is it always over 1? Or
Yes.
no matter what, always?
Yes. That's really important as we go to figure out transformations. Actually, later today, that over 1 will be really important for us. Okay? Forms of the equation. So there's actually 3, and we're actually going to see 2 of them today. One of them we're not going to see until after the break. Okay? So there's 3 forms. So write small. See if I can use a thinner marker here. All right. So one of them is called standard form. See, why doesn't it go any thinner? I don't know. Ax squared plus bx plus c. It's called standard form. And standard form's okay. We're going to look at that this morning. See if that works. Then this afternoon we're going to look at vertex form, which is our graphing friendly form. Okay? And that's y equals ax minus h squared plus k. This is called vertex form. So we got standard form, which we're going to look at this morning. We got vertex form, which we're going to look at this afternoon. And we've got intercept form, which we're going to look at after the break. So I'm using a capital R with a little subscript 1. and a capital R with a little subscript 2. And that's called intercept form. So those are our 3 forms. A line only had 2 forms, a parabola has 3, okay? And then we're going to go back up to our chart and find our first differences in our y column and our second differences in our y column. So first differences. To get from 9 to 4, I go down 5. Is everybody good with that? To get from 4 to 1, I go down 3. To get from 1 to 0, I go down 1. To go from 0 to 1, I go up 1. To go from 1 to 4, I go up 3. And to go from 4 to 9, I go up 5. So the first differences aren't constant. Does everyone agree with that? They're not the same. First differences aren't the same. So if I was just given a table of values and asked is it linear or not, if the first differences are the same, it's linear. If the first differences are not the same, we know it's not linear, but we don't yet know it's quadratic. So then let's look at the second differences. To get from -5 to -3, I go up to -3 to -1, up to -1 to +1. You see it's up 2 all the way down. So the second differences are constant. That's what makes it a quadratic. Okay? First differences are constant. It's linear. The exponent on x is 1. Second differences are constant. It's quadratic. Okay? The exponent on x is 2. And then when you get to grade 12, if you're looking at a cubic, it will be the third differences that will be constant. Okay? So we go down, fill that in here in our table. First differences, not constant. Second differences are constant. Good. Also, one thing I wanted you to know, we'll come back to it later, but we'll talk about it again. If the second differences end up being positive, your parabola is going to look like this. But if your second differences turned out to be negative, your parabola would be upside down. Okay? So if your second differences are positive, you get a right side up parabola. And if your second differences are negative, you would get an upside down parabola. Okay? That'll come out in the rest of the lesson. Okay. So then we're just going to go over the basic properties again. One special type is called a quadratic relationship. A quadratic relationship has an equation of the form y equals ax squared plus bx plus c, but it adds on that a can't be 0. And the reason it says that is because imagine if the number in front of x squared was 0, you have 0 times x squared and that term would be gone, and then you just get y equals bx plus c, which is a line. Okay? So that's why they have that written there. Sketch the parabola, see if you can do it from memory. So the vertex is 0, 0. Vertex is 0, 0. Step property from the vertex, over 1, up 1 on both sides. Then from your next point, over 1, up 3 on both sides. From this point, over 1, up 5 on both sides. And can we fit the 7 in? Nice. Over 1, up 1, 2, 3, 4, 5, 6, 7. We get our second chance at drawing it in. Vertex is 0, 0. Step pattern is up 1, 3, 5. Dot, dot, dot. Equation of axis of symmetry. There's something we haven't talked about yet. Axis of symmetry is also called the mirror line. So think about if you were going to fold that in half over the mirror line, where would the two halves line up on top of each other? Y-axis? Yep. So here's our axis of symmetry. It is actually a line. And we kind of briefly went over this the first week. Vertical lines have special equations. Their x equals whatever the x-intercept is. So the equation of the x-axis is actually, or sorry, the y-axis is actually x equals 0. Okay? Because it doesn't matter what y is, x is always 0. If you think about any point that's on the y-axis, x is always 0. Okay? So the equation of the axis of symmetry is x equals 0, 0, and the axis of symmetry is the mirror line. And when it asks you for an equation, you need to have x equals, and it'll be wherever the x coordinate of the vertex happens to be. Everybody good there? A little recap. We can determine if a relationship is linear or nonlinear by looking at the first differences within a table of values. A linear relationship has first differences which are constant. A relationship is quadratic if its second differences are constant, but not 0, because obviously a linear relationship, if the first differences were all the same, the second would be 0, which would be the same, but you already decided linear. Okay, so when you're looking at just a table, we're going to do the same thing we did here. And look and see, here we would go down 3, down 1, up 3. So it's not linear. We can already make that assumption. And then our second differences, up 2, up 2, up 2. So this one's quadratic, because the second differences are the same. Next one, first differences, we're going up 0.25, up 0.25 again, up 0.25 again, up 0.25 again. So this one is linear. And we don't need to worry about second differences if the first differences are the same. We know it's linear. Okay? Next one, we're going up 0.25, then up 0.5, then up 1, then up 2. So definitely first differences aren't the same. Second differences, we're going up 0.25. Next one is up 0.5. So already we know the second differences aren't the same either. So this one's neither. Okay, so it's not linear or quadratic. Something else.
What is it then?
It could be exponential, it could be cubic, there's so many things it could be, but we know it's not linear, not quadratic, we can cross them off, okay? It looks like it's exponential because it's doubling every time. The next one would be 8, right? exponential. For linear relationships, the first differences are always constant. For quadratic relationships, I'm just going to use the 2 with the little ND up there. Second differences are always constant. So here's where you need your calculator. We're going to look at given the graph in standard form, how could we draw a graph by making a table of values? And then from that table of values, we want to figure out what's the vertex, what's the step pattern, what's the equation of the axis of symmetry. Okay? So y equals x squared plus 2. Work here I'm writing just so you know what to enter into your calculator. So I'm going to replace x with -3. And this is what you would want to put into your calculator or your brain. Some people are really good at just doing mental math calculations. So that's going to be 11. So all I'm doing is replacing x each time, right, with the x value that's in the chart. So that's going to be 6. Remember, when you square a negative number, you get a positive. You know that in your heart. When you square a negative number, you get a positive. So there's our points. And then we need to plot them. So this x and this y form like an ordered pair, right? Everybody good? That's what we just did there. And then -2 and 6 would be a point. So you're just plotting those points now. Okay? So plot them, see what your parabola looks like. Here's my parabola. You guys have the points in the same spots as me. So all I did was plot -311, -26, -1302, 1326, 311. Okay, and then from this picture, what is our vertex? 0, 2, right? It's an ordered pair, so it's got an x and a y. So that point there, which is our vertex, would be 0, 2. Okay? Our step pattern, so to get from our vertex to our first corner, so from here to here, we would go over 1, up 1. Everyone agree? So over 1, up 1. And then our next one, we would go over 1, up 1, 2, 3 again. And then over 1, up 1, 2, 3, 4, 5. So our step pattern, we can say, got room under here. Our vertex is 0, 2. Our step pattern is up 1, 3, 5, etc. And our axis of symmetry is the y-axis again, agreed? That's my mirror line. And we know that that has the equation x equals 0. So axis of sim. Some people write AOS for axis of symmetry. It's fine with me. What's that short for? X equals 0. Okay, let's make sure we ticked off everything. We made the graph, we computed the table of values, we identified the vertex, step pattern, and equation of axis of symmetry. So we want to do the same thing for this one. So there's a negative in front of the x squared. Hopefully you're thinking that's going to make it go upside down, but we'll plot it and see if that's true or not. So that negative's out front of the x squared, so it's going to be negative bracket, and then I'm going to replace x with negative 2 in brackets, squared, plus 3. So if we follow BEDMAS here and we do the exponent first, when we square negative 2, we get positive 4, right? But then we're multiplying that positive 4 by the negative that's out front. Or you can think of it as having a negative 1 out front. So that's going to give me negative 4 plus 3, which is negative 1. So make sure you can put that into your calculator properly. It would be negative bracket, negative 2 bracket squared, plus 3. Negative bracket, negative 2 bracket squared, plus 3. And it should give you negative 1. Okay? Same idea here. So negative bracket, negative 1 bracket squared, plus 3. Negative 2. Negative bracket 0 squared plus 3. That's just going to be 3. This is wrong then, right? That should be plus 1. My bad. Yeah, negative 1 plus 3 is 2. 0 plus 3 is 3. Negative 1 squared plus 3. So it's going to turn into negative 1 plus 3, which is 2. Negative 2 squared plus 3. Negative 1. Negative 3 squared plus 3. Negative 9 plus 3. Negative 6. Negative 16 plus 3. Negative 13. Okay, try plotting those points. Negative 2, negative 1, negative 1, 2, 0, 3, negative 0. 1, 2. 2, negative 1. Oops. 3, negative 6. 4, negative 13. Can you see where the vertex is going to be from where the points are plotted? Yes, good. So 0, 3 is going to be my vertex. So if there's a point here, because of the mirror line, what do we know about over here? If there's a point 3 away from the axis of symmetry on this side, do you guys agree there's going to be a point 3 away from the axis of symmetry on that side? Because it's a mirror, right? And if you know there's a point 4 away from the axis of symmetry on this level, then you know there's going to be a point 4 away from the axis of symmetry on that level. Okay? Because this is a mirror. So if you look at the mirror and there's a point 4 away here, there's going to be a point 4 away there. So even though we didn't get every point in our table, we could use what we knew about quadratics to draw it in. And we figured out its vertex was 0, 3. Step pattern. So we're going the opposite direction this time. So our first step to get from the vertex to the next corner is over 1, down 1. And our second step is over 1, down 3. And our next step is over 1, down 5. And then our next one is over 1, down 7. So the way you write that out is that your step pattern is down 1, 3, 5, etc. Okay? Instead of up. And our axis of symmetry, or AOS, is still x equals 0. And the axis of symmetry could help you, especially when you're doing the table of values, to find your other points that are on the other side of the axis of symmetry if you don't use your table for all of them. Okay, we're going to get a different step pattern for this one, so that's fun. And I think for our last one, we're going to get our vertex isn't going to be on the y-axis anymore, so 2 fun things to look forward to. So when we're substituting in here, 2 comes out first, then negative 3 squared minus 7. And then you've got to remember back to grade 9 BEDMAS to make sure you can do that properly. So you square the negative 3 first. You're doing it in your head. 9 times 2 is 18, and then 18 minus 7. Or you can just key it in your calculator. 2 bracket negative 3 bracket squared minus 7. And you should get 11. Yep. Try filling in your table. Make sure you can do the calculations. draw the picture once you got your table filled out. Or you join the, check up at the front and see if you've got this in, like, other than 6 spots. And once you know it, draw it on there. Try to still make it a curve. I know it looks starting to look more V-ish, but it is curved as you can make it. Nice. Okay, I'll try mine here. Here's my vertex. Vertex is 0, -7. Everyone agree with that? What about our step property? Yep, from the first corner to the second corner, I go over 1 and up, 2. And then to get from my second corner to my third, I go over 1 and up, 6. We're pretty good there. And then over 1 and up, 10. So our step pattern is up, 2, 6, 10. How is 2, 6, 10 related to 1, 3, 5? Just double? Everyone see that? Where do you think that 2 comes into play in the equation? The 2 in front? So this number here is what determines our step pattern. Looking for a different color marker here with that one. So this number here, we call the step number, okay? That's called the step number. M was called our slope number in grade 9. A is called our step number in grade 10, okay? So our step property is always going to be either up or down, so that depends. But it's always going to be, our steps are going to be 1 times A, 3 times A, 5 times A, etc. 7 times A, okay? So once you know what A is, A determines your step number. And if A is positive, it's up. If A is positive, it's up. If A is negative, it's down. Okay? And our steps are always going to be the size 1 times A, 3 times A, 5 times A. Those are going to be the size of our steps. Okay? And our axis of symmetry is, again, x equals 0. Our AOS is the y-axis again, which is x equals 0. Okay, one more table to go. And this one's different because it has, we haven't done one with this dx term yet. That term's going to change our vertex from being on the y-axis to being somewhere not on the y-axis. Okay? And the calculation looks like it's going to be a little bit harder, and it is, but we should all be able to go and see that our a value is -2. Does everyone see that? So if I were to predict my step pattern, what would I predict my step pattern is going to be based on my new knowledge that we just came up with? Am I going to be like up or down? Down, because it's negative. And 2, 1 times 2, so down 2. Down 3 times 2, which is 6. And down 5 times 2, which is 10. That's our prediction. Okay, and then we're going to see if that happens when we fill in our table and draw the graph. Okay? I'm going to use my calculator for that one. Just -10? I should write it in. For the viewers at home. Zero. Six. Eight. -6 and -10. -5 and 0. -4 and 6. -2 and 6. And 0, 0 and -10. And do the points still look like that? Once you've got your points sketched in your parabola. Okay, so So this time, our vertex is -3, 8. So the vertex is -3, 8. We're checking to see whether our step pattern is right. So we predicted over 1 down 2. Is that right? Over 1 down 6. Is that right? And over 1 down 10. Yeah. So our step pattern is down 2, 6, 10. And our mirror line is not on the y-axis this time. It's right through the vertex. It always goes right through the vertex. Since the x-coordinate of the vertex is -3, the equation of that line is x equals -3. Okay? So our axis of symmetry, it always goes right through the vertex, is x equals -3. That -3 relates to the -3 in our equation of our axis of symmetry. Okay? Notice that in the equation y equals ax squared plus bx plus c, the c value always turns out to be the y-intercept of the parabola. So our c value was -10, and if you look at where does the curve touch the y-axis, it's at -10. You see that? And if you go back, the c value was -7, and that's where our vertex was, but that was also where it touches the y-axis. Okay? And if you look back at these ones, our c value is 2. C has no x with it, remember, so that's how we know it's the c. And our y-intercept, which is also our vertex, is at 2. Okay, why is that? Well, if you remember back to grade 9, when you find the y-intercept of something, it happens when x equals 0. The y-intercept happens when x equals 0. And if we were to put x equals 0 into this equation, it doesn't matter what a and b are. If you're multiplying them by 0, they're going to become 0. Everyone agree with that? So you're going to end up getting 0 plus 0 plus c, or c. So the y-intercept is always the c value. Okay? So let's add that to our chart paper here. So this tells us two things. Definitely not as graphing friendly as the one we're going to learn later today, but we do know the step pattern, and we also know the y-intercept. So standard form tells us two things. Two important things, but it would be nicer to know the vertex and not the vertex. Okay? All right, so I'm going to stop recording. You just